So just to introduce myself, my name is Chris Baczynski. I specialize in aircraft propulsion. I'm a DAR for both engines as well as aircraft power plant installations and in addition noise. So I've been lucky to have been a participant on several aircraft electric propulsion projects, including engines. Foremost of all, key DER equivalent for magnex. Also, I've been working with Kite Magnetics in Australia and Duxon, which is a very interesting Canadian company, plus some other work. So really, the focus of this presentation, or the context, actually comes from the engine side. Now, that context needs to be communicated and applied to the aircraft side, where I am involved in several different projects, most notably the CAE Electric Power Generator 3 as part of the LSN-led team, which is a subject of the next presentation jointly with LSN as well as Harbor Air. So for this presentation, I will not talk about the aircraft side so much as I will talk about the lessons from engine certification side. Specifically, the intent is to share some key findings from Part 33 work. It's not intended as an exhaustive exercise. The focus is just on the selected aspect. And just in terms of the context, when by electric engine versus a motor, I mean here, as defined now in certification literature, it's both the motor control unit, plus any power electronics, interconnects, and any other systems that may possibly form the part of the engine type design. For example, if you have a liquid cooled system, it could very well be your oil network that is, or at least a part of it that is certified as under the engine type certificate. First, just to set the basis, no pun intended, the certification basis for electric engines is based on entirely on special conditions. Unfortunately, EASA and the FAA have approached the subject slightly differently. So on the EASA side, we have SCE19, special condition for hybrid electric and hybrid propulsion system, or EHPS, and this is a generic special condition. Initially, there was some expectation that they'll have a product-specific one as well, but that did not happen. So this is the EASA special condition is a very high-level one. It's really based on CSE in the end. If you actually compare the text, the headings, it's basically most of the headings are the same as the standard CC code, but it's been extremely generalized to be like really performance-based to the maximum intent possible. So it's really objective-based, and obviously it's intended to cover hybrid propulsion systems. By propulsion systems, we really mean an engine plus other components as an extended engine type certificate rather than an aircraft installation. It does have one provision for electrical power generation and one provision, only one, for propulsion battery. So it's not very specific. Whereas on the FAA side, we have a number of product-specific special conditions. Now, in reality, they're pretty much all the same, with the exception that after the first one was issued for magnex, the FAA, when based on the outcome of the discussions that we had, and the FAA decided for subsequent programs they're going to basically add some additional content, just for clarification. In other words, what magnex has already accounted for in the certification plan, other applicants argued that, well, they're not required because the special condition doesn't say so explicitly, so the FAA made some modifications to update the text. As I was saying, the Magnex was the first one to be published, followed by Beta and Safran. There are also special conditions for Joby and Archer eVTOLs, and these are included in notably as part of the aircraft, meaning under the subpart H electric engine requirements, rather than as standalone products. The FAA version is really a generalized Part 33 code, and like EASA, it actually picks up turbine engine requirements with additional content. It's not, however, as high level as the EASA one. In some cases, it might actually be the same requirement as the FAR, with the number removed, power response, for example. There's also numerous references to FAR 33. There is no coverage in hybrids. It's only strictly for electric engines. However, for hybrid, there is the work that we're doing with NASA, which on the hybrid propulsion gap analysis that's both for the special condition as well as for the standards. But that's a subject for another session next year or a few years. Anyway, why this introduction? Well, we did a detailed gap analysis with Magnex comparing these special conditions, and we found out that out of the 33 top-level paragraphs in the FAA, only 7 were really equivalent to the EASA content. So here's some examples. I'm not going to go through each and single one, but just to visualize or quickly explain the potential impact on aircraft while fire protection. There is arguably a significant gap in the EASA version, at least in my view, when it comes to coverage of liquid-cooled engines. It's clear that it was the EASA SC was addressed with air-cooled engines in mind. Now, EASA, I'm sure, will argue that yes, they do have the necessary provisions, but for liquid-cooled engines, but not nearly as much as FAA. So there is a gap that needs to be harmonized. Containment is another case. FLA allows margin of burst approach, EASA doesn't, but more importantly, EASA requires containment of high energy debris. FAA requires containment of any debris radially, but allows axial non-containment. So depends how the engine applicants ends up showing containment. Questions can be raised, well, what about rotor burst? Do we need to protect it or not, right? And that depends on the individual methodology. But we do have a gap which allow a little bit of misharmonization here that could impact the airframe. Another one, temperature limit approach. EASA applies that requirement only to ratings with a duration of less than 2 minutes. FAA mandates its requirement for all ratings, irrespective of duration. So how to bridge that gap? Well, there is the work that, there is the hope, rather, that in spite of the significant differences in the wording of the special condition, harmonization can be achieved at the standard or recommended practice level. However, there's high potential, in fact, of things going the other way. I'll give you 2 examples. One, we do have a joint SAE and EUROK working group putting together the guidance on durability. Myself and my colleague Eve are quite deeply involved in that. And that is actually will be going to a ballot soon. This has been a fairly successful harmonization exercise in that basically the same text will be published as both FAA and EASA, as both EUROK and SAE document. On the other hand, we do have another example where we had for endurance, and again, our TCCA colleague was leading the effort for a recommended practice. Our UK friends decided to come up with a completely different document, which, in my view, has a lot of errors in it and gaps. So this would be a case of current issue where containment was not achieved. There was recently an ASD paper on EHBS harmonization that was presented to CMT. I can tell you this was another example of difficulty of harmonizing. As the sole Canadian on the group, joined with a couple of my friends from the US, we actually argued that we should highlight every single difference and include the verbatim gap analysis that we did, and that rather than tasking the CMT, we should actually be providing a solution. We were not successful in that. The Eurocentric viewpoint driven by Safran has prevailed. Again, this shows some difficulty that even when talking about harmonization, we can't really harmonize in that way. The gap is still quite large. So what are the lessons learned? Also, there remains a risk. At this time, until these issues are resolved, there is a risk, there remains some risk of non-acceptance when it comes to foreign validations. And that goes both ways. Either non-acceptance might be a harsh word, but let's call it delays or significant effort. Second, when procuring electric engines from across the ocean, have the company, have the aircraft engine OEM actually commit that they'll take responsibility for the validation. Because if you don't, you'll end up having to expend significant resources of your own to potentially bridge that gap. Then finally, different outcomes, different detailed differences between those special conditions and their implementation could also result in different outcomes at the aircraft level standards. One example is fire protection, and that's something that we'll go into next. Okay, so let's have some fun with this. This is an engine and power plant fire protection debate that's going on. We could be talking about fire for the whole day, so I'll try to make it as brief as I can. Basically, in traditional engines and as well power plant fire protection, the threat is dominated by flammable fluid threat. It's not the only one, like combustor burn through, etc., but it's the main one. We do have a designated fire zones for engine installation, as well as definition of general fire zones based on the presence of a nominal ignition source and flammable fluids. So basically the point is we do use we use a standard burner. The same standard burner is used for fireproof, fire-resistant testing. The difference is 15 minutes for in case of fireproof, 5 minutes fire-resistant. The flame itself is well defined as 2,000 degrees Fahrenheit minimum, 4,500 BTUs. You got a heat flux requirement, etc. Real fires, of course, can be smaller or bigger, but this is what has worked historically in the past. The one on the top. Now, in case of electric engines, if it's an air-cooled engine, you don't have any flammable fluids. If it's a liquid-cooled, well, we'll get to that in a minute. So a proposal has been made, in fact, it's already been published, for a new type of fire zone, rather than a designated fire zone, to have a fire withstanding zone. That would have a lower level of protection compared with DFC. The question is, what exactly? Well, our friends at EASA already have published, or already have used their specific requirements. These are based, in their case, on DL 160, Section 26, Category C, or flammability testing. So the basic appendix F. So those of you that work in the occupant safety field, are quite familiar with flammability issues. And so here we're applying basically what has worked well in aircraft interiors to electric engine installations. Now the flame has been defined, the flame that is being used is the Bunsen burner flame, 1550 degrees Fahrenheit for 16 seconds. It can be horizontal, 45-degree burn test. However, this is really based on arguments and experience. Now that experience comes from electrical system installations in aircraft cabins, really. So in the West, there is being, in North America, should I say, there's been questions being raised if this is really adequate for high voltage devices, given the power levels and given the energy levels. Now here is a good comparison of the flame. Okay? Here's a traditional power plant flame. Here what is Bunsen burner flame that is being proposed. So temperature aside, it's really the volume, the intensity, and basically the heat flux, right? So there is some arguments behind that, but the point is there is currently a significant debate whether or not this is sufficient. And we may end up having to differentiate between threats to the engines versus threats to the airframe, because fluid fire is no longer present. So in other words, in a traditional engine, you might have a leak in an ignition. There is, say, a pooling fire from the cowling. Here, with an electric, if the threat is coming from the engine itself, rather than from outside of the engine, well, if the engine is, if an event happens that destroys the engine, well, you don't necessarily need to protect the engine against to make sure that it functions. You just want to make sure that continuous combustion doesn't add to the hazard. There's also a need to preclude common cause events with an electric engine fire leading to, say, battery thermal runaway if they are in proximity, and vice versa. You don't want a thermal runaway necessarily in one module to shut down your entire propulsion system. For oil-cooled engines, other than hybrids, note that unlike traditional propulsion engines, there may not be a nominal ignition source, meaning for the type of fluid present. So, for example, oil has a very high upper ignition temperature, very high hot surface ignition temperature, etc. So, at normal operating temperatures, electric engine components, their max temperature is well a few hundred degrees Fahrenheit below that of what would cause the oil to ignite. So, you may ask, what about other type of fire-like events? Well, one event, one lesson learned that we found out with one of the applicants has occurred during development work. Actually, I would call it more failure mode effect demonstration testing. So it was done under condition of simulated failed protections, because obviously protections can fail, so we need to know what happens. Unfortunately, there were no thermocouples installed to characterize the flame. Mind you, the component has been redesigned anyway to minimize this type of failure altogether, despite that it was a test simulating protection failure. So basically what we have seen in the module, with the protection deactivated, in case of a power module overload failure, there is a rapid temperature increase. That causes a flash event that basically ignites or results in an ignition of the other power modules in the unit, leading to a rapid internal conflagration. So no detonation, basically, but still a fire event. It has, as I said, a cascading effect on the other power modules. And so basically, within a few milliseconds, the entire content of the box can be destroyed. In this case, the shutdown was about 3 seconds into the event. I was really hoping to have some pictures to share with you. Unfortunately, I did not get the clearance from the client to present them. So So unfortunately, we have to stick with my poorly drawn charts. So basically, the mechanism was that we had an extremely rapid generation of combustion gases and byproducts. This led to a rise in internal pressure. This rise and pressure rise was simply too rapid to allow evacuation by a vent hole. And even if you made the vent hole larger, the same thing would happen. Basically, you would have to have an open vessel, really, like basically a complete open wall. This led to the upper lid being heavily deformed, but it was maintained. There was actually a rupture, a hole in the side of the casing, about 2 or 3 inches in terms of surface area. And this was due to a combination of pressure melting and correspondingly ejection of high temperature, high pressure gas and combustion byproducts. Now, what's important to note is, in this case, there was no flammable fluid ignition. It's simply because of the direction of the ejectants. That is a function of the design. Right? So in this case, there was no penetration of the wet area, simply because of the nature of the separation, and so-called wet plate, rather. That was separating the cooling compartment from the power electronics. However, in the case of another design, it could very well easily have led to a flammable fluid fire as well, which means that the zoning and the protections you need at the aircraft level may ultimately have to depend on the susceptibility and characteristics of the individual engine, which category it falls into. There was a fan-type flame with an extent that partially obscured by a large amount of particulate matter ejected. And it was quite significant in that it would be able to reach the cowling and affect a good portion of the zone in terms of temperature. Although temperature and pressure K as functional distance were not measured. Excuse me. Again, we did notice residual flames, smoldering, edges of show effects of melting. The overall damage to the unit was basically catastrophic destruction of power electronic. However, the wet area, basically the area where you had the oil cooling system, remained completely intact. The quality of the, I've judged, having done an on-hands inspection, I've judged it to be comparable to about a 5-minute fire-resistant test on a FADEX. Obviously, the direction was, the flame direction was, in this case, from the inside rather than from the outside, but basically the overall level of destruction was comparable. The duration of the event was really seconds, except for the residual flame. However, the temperatures, although unknown, suggest that the nature of melt damage is in excess of 2000 degrees. So the extent and size of this event can be closer to what we actually see in traditional combustion power plant burners. Certainly not the type of Bunsen burner type that I was showing before. So, conclusions, well, power modules can result in high energy release. The scenario is equally applicable to both pure air-cooled and liquid-cooled electric engines, and engine-authorized applicants need to consider cascading failures when assessing this. For part 23, well, we have to consider this event as a possibility, and interestingly, when it comes to electric engines using flammable fluids, even if there is no known ignition source, we would still want to have them demonstrate that there is no common cause or cascading failure that could result both in a release of flammable fluids and the ignition. And if there is really Further data is actually needed and if we want to characterize this event. But the key question for us is whether to design or protect. Well, if it is something that can be completely designed out at the engine level, then we no longer may need to cater for it at the aircraft level. But if there remains a chance, at least a reasonable chance, let's say 10 to the minus 6 as an example, then we may end up having to protect it against it. So this is a question for the regulator to answer. What I can tell you is I think this is something that we should at least consider unless the engine applicant can positively show that no such event can take place. Now, another lesson learned from other programs is continued rotation. Basically, both FAA and EASA special condition require that if the engine continues to rotate after a shutdown, as in the case of a windmill, there should be no hazardous engine effect. What was found is that continuous rotation, as basically windmilling with a prop, under the presence of a short circuit fault, can result in molten metal particles, other debris, sparks being ejected from a power electronic compartment. In addition, there is a propagation of high voltage to low voltage via plasma arc. So this would need to be addressed ideally by some kind of fast-acting disconnect mechanism, and at the same time, worst-case parameters for the resultant ejecta are being defined in the installation manual. And a couple of other lessons learned from we do have a Canadian-specific advisory I see about ignition sources. This dates back to issues that we had with starter generator failures, where basically there were debris, pieces of winding, etc., that were ejected. We also had observations in terms of containment testing, for example, flame blade out test, that yes, you can have a fire as a result of a FBO, even if you're contained, simply because of, let's say, shock loads that can damage your oil system. So the bottom line is engine applicants who use containment requirements, who show compliance by analysis only, as opposed to a test, may, other than those that use margin to burst approach, may actually miss these potential failure risks. Now, LOPC, well, I'm being told that we actually have, 10 minutes left, or less than that? 10 minutes. So this is a fairly contentious topic. We'll cover it in more detail at the aircraft level in the next presentation. But just to clear up the air for some of us who are aware of this issue, the existing regulations for engines require control systems to be essentially single-fault tolerant. The same expectation was applied for fault accommodation, has been applied to the electric engines for electrically detectable and electronic failures. And the problem was that the first generation of electric engines were not able to meet that single-fault accommodation goals. Simply, it was difficult because the level of high voltage and control system integration. It's the fact that the scope of the rule was expanded, for example, to include the windings, made things even worse. The point here is that both industry leaders were trying to come up with an alternate way to comply with this requirement, because otherwise they couldn't get their engine certified. So CMT was really set up as not a rulemaking, but a harmonization activity to allow a common approach between EASA and FAA. And I think they, in the process of coming up with their findings, CMT, EHPS, TST got a lot of heat, but it was really a harmonization. So basically that's where the single fault ratings are. Now, there we do have some lessons learned. there should be more coordination between the engine the engine side and the aircraft side when it comes to issues that affect the installation. Also, not every single fault rating has to be called an emergency. And in case of the rated engines, like in another program that is being presented here, it could actually reduce this power loss to within below 15% or below minor power loss. So what's being done right now? Well, we're going to talk separately about addressing this issue at the aircraft level, but on the engine level, there is work ongoing, different approaches. One of them is segmentation. For example, if you have 8 inverters and winding sets, you're only going to lose 12.5% if any one of them fails, which is below NPL. There are some companies that are trying to apply redundancy, and there's different approaches to that. Then, of course, there's the T-rate. The bottom line is these LOPC and the resulting single fault ratings are with us for the first generation of electric engines. In the future, we can hopefully reduce that or design them out. Another quick lesson learned, we found out that electric engines can be extremely sensitive to high voltage power and quality requirements. Now, these are will be identified verbatim in the engine installation manual as a differential mode voltage ripple. And you might think that, well, lithium-ion batteries are DC devices, but but there's still some noise and ripple. Plus, you've got other power electronics in the loop, and that is enough to cause issues. So what we've seen with one engine applicant is actually not all aerospace grade cells are the same. So the lesson learned for the airframe is basically make sure that you can actually meet the power quality requirements at the aircraft level when considering your batteries and when you're designing your ESS. Another interesting issue. We found out, at least in some cases, that declaring a dedicated takeoff power rating may not be practical. The power electronics will basically be so limiting that it actually, a rating like that would be of too short of a duration. And that's fine. That's quite similar to what we see in some reciprocating engines. However, what's interesting is that some other engine OEMs are declaring takeoff power ratings that are shorter than the standard 5 minutes time. For example, 3 minutes on one of the Safran units. I've seen a takeoff power rating being proposed as short as 90 seconds. Now, technically, FAR does allow that. CFR 1.1 defines takeoff rating as not over 5 minutes. There is a provision for the extended takeoff rating of 10 minutes. So technically there is a case to do that, but we have to ask, how does it affect the equivalency of the safety being equivalent to existing fleet? So at this point, until this is resolved, the recommendation is for airframers to coordinate with the engine OEMs to ensure that if you're planning to use a shorter end of rating, to make sure that it actually fulfills not only the wording, but the intent of the aircraft level standards, and including takeoff and climb performance. Last but not least, we do have an operating range restrictions. I've shown here 3 types. The green type, basically, is you do have constant power over your voltage range. The blue line is something that certain European designs currently feature, is you do have an abnormal range where basically below a certain threshold, voltage threshold, you do have a linear drop of power. So that has to be accounted for. And finally, some of you have seen something like the red line, which shows the power gradually decreasing with a voltage. That's actually, I think that's problematic for the aircraft, but honestly, I would question if that's certified, if that is indeed even certifiable for Part 33. So, just for some parting words, just a reminder, we do not compete on safety. So disclosing safety relevant data is in everyone's best interest. Simply why? Because accidents affect public perception. And that public perception turning to fear or distrust has the power to end some interesting technologies or operations. Now these examples here were not even novel. Hindenburg was supposed to be initially filled with helium. It just, there were actual export restrictions. Likewise, the New York Airways had been operating for years successfully before this accident happened, and this was a landing gear. So not even new technologies, yet they ended the era of the respective operations. So if we're thinking about electric, for example, VTOLs, well, we have to all work together to make sure that to prevent an accident. Because a high visibility, high profile accident can hurt everyone in the industry. Okay, thank you.
Thank you.
That's a fantastic.